The air inlet connection mounts to the side of the cylinder head. The intake manifold is integral to the cylinder head casting. The fins of the ECM cooling plate install into the intake manifold. The intake air flowing around these fins cools the electronics in the ECM. Signature engines use a wastegated turbocharger for better low engine speed performance and control of high engine speed boost. The term wastegate comes from the fact that with this style of turbocharger, some of the exhaust gas is gated around the turbocharger turbine wheel, and the exhaust energy is wasted. That is, the exhaust energy is not used by the turbocharger compressor wheel to pump intake air into the engine. The wastegate is a normally closed valve in the turbocharger that allows a controlled amount of exhaust gas to bypass the turbine wheel. By opening or closing, this wastegate valve varies the intake manifold pressure within a desired range. On a non-wastegated turbocharger, boost is proportional to engine speed at wide-open throttle, as you can see from this chart. If we wish to increase airflow at lower engine speeds or torque peak power, we could use a higher capacity turbocharger. However, this turbocharger results in more boost than we need and excessive cylinder pressures and temperatures at rated speed. Using a turbocharger that produces the additional desired boost at torque peak speed and wastegates the exhaust gases from torque peak to rated speed obtains the desired boost for the entire engine operating range. The goal of a wastegated turbocharger is to keep rated speed power constant but provide better acceleration, provide quicker response at lower engine speeds, and provide the additional boost needed at torque peak. A wastegate actuator controls the position of the wastegate valve depending on the boost pressure it receives. The actuator is a canister with a rod. One end of the rod is attached to a bellows inside the canister, and the other end is attached to the wastegate valve. An internal spring in the canister applies force to close the valve. Turbocharger boost pressure applies pressure to one side of the bellows and tries to open the valve. This force is opposed by the internal spring in the canister. The wastegate valve position is determined by the balance of the boost pressure force opposed by the spring force. When turbocharger boost pressure on the bellows is greater than the opposing spring pressure, the wastegate opens to let exhaust gas bypass the turbocharger turbine wheel. When boost pressure decreases, the spring closes the valve. Because the turbocharger utilizes a dual entry port, the wastegate only bypasses exhaust gas from the rear three cylinders around the turbine wheel. The four-step wastegate controller mounts to the air inlet connection on the signature engine. This device controls the boost pressure delivered to the actuator in 4 distinct steps. This 4-step control provides improved control of boost pressure. A table stored in the ECM is used to determine the desired wastegate step for the current engine speed and commanded fueling. The ECM sends signals to the 2 wastegate solenoids to place the wastegate controller in the desired step. This provides a better match of airflow to the current engine speed and fueling. The 4-step wastegate controller consists of a wastegate pressure control block, inlet solenoid, and vent solenoid. 2 inlet orifices and 2 vent orifices are installed in the control block. Each of these orifices is precisely sized to allow the desired amount of flow. One of the inlet orifices is not affected by the solenoid position. This orifice provides a flow path for boost pressure to enter the control valve at all times. One of the vent orifices is also unaffected by the solenoid position. This vent allows some air to vent from the control valve at all times. Let's take a look at how 4-step wastegate control operates. We will begin with step 1 of 4-step wastegate control. With the inlet solenoid energized and the vent solenoid de-energized, the intake air at the control valve flows through both of the inlet orifices. A small amount of air vents to atmosphere through the open vent orifice. The majority of the airflow is directed to the wastegate actuator. This controller position provides the maximum airflow into the control block and vents the minimum amount of air to atmosphere. Since the intake air pressure is used to open the wastegate valve, this controller position opens the wastegate valve at the lowest boost of any of the 4 steps. In the second step of wastegate control, both of the solenoids are de-energized. With the solenoids in this position, intake air flows through the one open inlet orifice into the common passage. Part of this airflow passes through the open vent orifice. The open inlet orifice allows more air to enter the control block than can exit through the open vent orifice. The remainder of the airflow in the control valve is directed to the wastegate actuator. This controller position provides the minimum airflow into the control block and vents the minimum amount of air to atmosphere. At this step of boost control, additional boost is available as compared to step 1. With the third step of wastegate control, both of the solenoids are energized. With the solenoids in this position, air flows through both of the inlet orifices into the common passage. Part of this airflow passes through the 2 open vent orifices. The remainder of the airflow is directed to the wastegate actuator. In this position, the maximum airflow is allowed into the control valve and the maximum amount of airflow is vented to atmosphere. At this step of boost control, additional boost is available as compared to step 2. The fourth step of wastegate control requires the highest boost pressure to open the wastegate valve. In this step, the inlet solenoid is de-energized and the vent solenoid is energized. With the solenoids in this position, the flow through the inlet orifice exits the control block through both of the vent orifices. More airflow enters the one open inlet orifice than can vent through the 2 open vent orifices. The remaining air not venting to atmosphere is directed to the wastegate actuator. In this position, the minimum airflow is allowed into the control valve and the maximum amount of airflow is vented to atmosphere. In this position, the minimum boost pressure is directed to the wastegate actuator. This controller position results in the maximum available boost. This chart summarizes the solenoid position and the resulting airflow for each step of 4-step wastegate control. Tampering with the 4-step controller will not increase engine power and it can reduce fuel economy. In addition, the excessive boost may result in engine damage. Each of the 4 orifices in the wastegate controller is precisely sized to provide the desired airflow in each of the 4 steps. Do not use a metal burnisher on any of the orifices or the resulting rate of boost pressure flow may be incorrect. The ECM uses an algorithm based on engine speed to determine the desired step. This algorithm is designed to prevent the ECM from cycling between steps too frequently. The exhaust manifold is relatively short compared to other engines. This design improves the thermal efficiency of the manifold. Airflow in the signature engine begins as the intake air is drawn through the air cleaner into the turbocharger by the compressor wheel. Compressing the intake air causes it to heat up. After leaving the turbocharger, the hot intake air flows through a large pipe to the charge air cooler located in front of the vehicle radiator. The ram effect of the vehicle and the coolant fan cause ambient air to flow around the tubes, carrying the intake air across the cooler. Heat from the intake air is transferred to the ambient air flowing around the fins of the cooler, thus decreasing the temperature of the intake air. The use of a charge air cooler provides lower intake air temperatures, increases engine power, and reduces engine emissions. After passing through the charge air cooler, the intake air enters another large pipe, which allows the air to freely flow into the intake manifold. From the intake manifold, airflow continues to each of the cylinders. When a cylinder's intake valves open, air flows into the combustion chamber. After the valves close, the upward movement of the piston compresses the air in the cylinder. Near the top of piston travel, fuel is injected into the compressed air in the cylinder, generating combustion. After combustion is complete, the piston begins its upward stroke. This forces exhaust gas out of the cylinder past the open exhaust valves. Exhaust gas then flows into the exhaust manifold and into the divided entry turbine housing of the turbocharger. In the turbine housing, the exhaust gas drives the turbine wheel. Since the turbine wheel and compressor wheel are on a common shaft, the motion of the turbine wheel causes the compressor wheel to turn, which pulls intake air into the turbocharger compressor. The air inlet for the air compressor is connected into the intake manifold through a fitting in the bottom side of the cylinder head. The air compressor outlet connects to the vehicle wet tank to supply air for the vehicle systems, including the service brakes. If the engine is equipped with an electronically controlled air compressor governor, the ECM controls the operation of the air compressor to optimize fuel economy. This is done by operating the compressor in light load situations.